the previous lecture I was discussing a two-dimensional band structure and also came to the idea of density of states simply because the number of states are just too many and it is very difficult to look at each one of them, and it is much better to actually look at what is how many states are there at every energy value. So, that was given by D of E, and of course, you can also use it in one dimension. I will talk about more of this one later on, but right now I want to give you a little bit of a feel for this density of states. So, supposing let us look at two different structures. So, there is a structure 1, I am just giving you an arbitrary structure, and then a structure 2. So, supposing the density of states of the valence levels in structure 1 is like this, and the density of states of energy levels in structure 2 is something like this. The question is, for the same number of electrons, for the same number of valence electrons, which structure is more stable? This is the question. So, what you will see is the following, that is, the number of electrons is fixed. So, the area under the dE versus E curve up to E max must be the same in both the cases. That is, in structure 1 I go up to E max 1, in structure 2 I go up to E max 2, and in both cases the area under this dE curve must be the same because the number of electrons is the same. So, if you look at structure 1, let us say that the E max is this one, structure 1. In structure 2, to have the, so this is the area, so this tells me how many electrons are there in the system. So, in structure 2 I have to go to E max, which is structure 2, to get the same area, that is to fill the same number of electrons. Now, you see that in structure 1 the total electronic energy is much smaller, because the highest energy level that is occupied is EM1 and all the lower energy levels are occupied by more and more electrons. Whereas, in structure 2 the highest energy is E max 2, which is greater than E max 1. So, because of that fewer electrons are there at the lower energy levels, and there are more, and as you keep going up they start populating the higher energy levels. So, electronically structure 1 will be preferred over structure 2. Okay, so, now let us see, is it sensible to talk about the number of electrons varying between I mean rather the number of electrons that are being occupied per atom, which is the total number of atoms. Is it possible to vary it? That is, can we vary electron atom ratio, that is the number of electrons per atom ratio. So, this is actually electron atom ratio, not atoms. Well, it is possible. For example, let us look at the case of copper and zinc. The number of 4s electrons in copper is 1, because the electron configuration is 3d10 4s1, and number of 4s electrons in zinc is 2. So, if I have a an alloy which is of copper and zinc, okay, copper and zinc alloys are known as brass. Okay. So, if I have a copper zinc alloy, then what you will have is if 1 minus x, if in the proportion 1 minus x atoms of copper and 1 atom of x atoms of zinc in every unit cell, let us say, then this will have the number of electrons will be 2x plus 1 minus x, this is number of per atom, this is what you have, or it is 1 plus x electrons per atom. So, if you keep changing the composition of the alloy, then as you keep changing the composition of the alloy, then you are changing the number of electrons to atom ratio. Well, what does this got to do with it? What happens is that in these systems it is known that as you keep changing the composition X, or you keep changing the electron atom ratio, then the structure of the alloy changes. Okay? And this was explained first by Hume-Rothery, and Hume-Rothery is of course a single name. Hume-Rothery. He was one of the early metallurgists from Oxford to actually use quantum mechanics and energy band theory to understand metallurgy and alloy systems. So, according to him, what he said was that the preference depends upon the density of states curve in each structure. So, copper zinc can have, for example, an alpha structure, I think it is alpha, which is actually a body centered cubic, or it can have, I think the other one is a beta structure. You can actually look up a very nice book that he has written, which is a theory of atoms and metals or something of that kind, and it is a Dover publication, and it is as though there is a conversation that is going on between a young scientist and an old metallurgist. So, the young scientist is trying to explain to the old metallurgist all the concepts of quantum mechanics and how it can be applied in metallurgy. Okay, that is just an aside. So, if you look at the beta structure and the alpha structure, the BCC and the FCC, FCC has a peak in density of states at a lower energy than BCC. So, if I plot density of states versus energy, then what I will find is for the say for a FCC structure it will be something of this kind, but for a BCC it will be slightly different. So, it will go, so this will be the BCC. So, what you see is that the BCC has a peak in the density of states at a higher energy than FCC. So, what it implies is that for low electron atom ratio, FCC is preferred over BCC, but at higher electron atom ratio, BCC is preferred over FCC. So, there is a phase change, there is a change in structure from BCC, rather FCC to BCC as the proportion of zinc is increased. In the alloy. In fact, one can if one knows the Brillouin zone structures for the BCC and the FCC, it is possible to actually explain why you should have peaks coming at higher energy in case of BCC compared to FCC. I think we will have some occasion to talk about it probably in this course. Well, now let me go over to 3-dimensional systems. Okay, of course, this is also a 3-dimensional system, but I am talking about energy bands in 3D systems. So, in 3D systems you have 3 primitive translation vectors which are A, B, C, and we have to write down the tight binding wave function in this particular case very simply as follows. We can say, for example, the lattice translation vector Rn is equal to, let me call it instead of n, just to emphasize the fact that there are 3 integers which define the lattice translation vector. So, let me say this is R L M n. Okay. This is equal to L times A plus M times B plus N times C. So, if I write down the tight binding wave function, as before, say for the orbital phi of r, then we have psi k of r is equal to sigma over L m n e to the I k dot r L m n phi of r minus r L m n. Now, you see that this is now actually running over all the atoms in the along the A axis, which is defined by the index L, all the atoms along the y axis or the B axis defined by m, and all the atoms along the C axis defined by n. So, this is one of the tight binding wave functions that one can write, and this has to be a single valued function. And this imposes the condition that change in k to k prime equal to k plus some vector capital K, let me say, some vector capital K should be such that e to the power, if it satisfies this condition, e to the I k plus k k times R L M n is equal to e to the power I k dot R L M n, then the new k value, the new k prime equal to k plus k is superfluous, in the sense that it is going to be describing the same state as before, and this can happen if this is true, if k dot RLMN is equal to some 2 pi times integer. We saw that in the case of the one dimensional system, where if I added 2 pi by a to any value of k, then e to the power I k n a was equal to e to the power I k prime n a. So 2 pi by a was the reciprocal lattice vector, and changing k by 2 pi by a does not change anything. So, we always, this allowed us to confine the k values to minus pi by a less than k less than or equal to pi by a. Now, how can you do that in a 3 dimensional system where a, b and c are not necessarily orthogonal, in the sense that a is not along the x axis, b is not along the y axis, and c is not along the z axis. And it is also possible many a times that you have a system in which the Bravais lattice of the solid is something like either a BCC or an FCC, in which case first thing you have to do is construct the primitive cell, and from the translation vectors of the basic primitive translation vectors of the primitive cell, you have to construct the reciprocal lattice space. So, for example, let me look at the case of the FCC lattice. So, if I look at the FCC lattice, if I write a figure for the FCC lattice, let me try. So, we have atoms at the cube corners and the face centers. So, that is the FCC lattice. And there is one in front as well. So, what you are seeing here is there are 4 atoms per unit cell, 4 atoms, actually 4 lattice points. Per unit cell, but what we really require is to construct a primitive cell which has only one atom only in the unit cell, so how do I construct it? It is quite simple. So, this is one side, this is another side, this is another side. So, there are 4 of these and there are 4 of these as well, and this is in the front face. Okay, so, this one is in the front face, this one is in the back face, and now I will have to join up. Okay, so, I can join this and this, I will get one face, and then I will join this and this, I will get another face, I will join this and this. So, I think I have now got the the proper rhombohedron, which is the primitive cell. Okay, so, let me just highlight that. Okay, so, that is a primitive unit cell, and once I have the primitive unit cell, then what I can do is I will construct reciprocal lattice translation vectors. I construct the reciprocal lattice translation vectors as A equal to 2 pi times B cross C divided by A dot B cross C, B equal to 2 pi times C cross A by A dot B cross C. We know that A dot B cross C is the same as B dot A cross C is the same as C dot A cross B, and then I have C which is given by 2 pi times C goes to A cross B by A dot B cross C. Now, having done that, you can now show that A dot A is equal to 2 pi, because the numerator and the denominator become the same if you take out the factor 2 pi, and we have A dot B is equal to 0, because B dot B cross C is equal to 0, and A dot C equal to 0, and similarly B dot A equal to 0, B dot B equal to 2 pi, and B dot C is equal to 0, and C dot A equal to 0, C dot B equal to 0, C dot C is equal to 2 pi. So, these A, B, C now become capital A, capital B, capital C now become the reciprocal lattice translation vectors. A, B and C are reciprocal lattice translation vectors, which means that I can have a reciprocal lattice translation vectors. I use LMN, so let me use it as PQR is equal to P times A plus Q times B plus R times C is a reciprocal, these are primitive vectors, okay, reciprocal lattice primitive vectors. I should not have said translation vectors here, these are primitive vectors, and I have PQR are integers, and KPQR is a reciprocal lattice translation vector. It is not a primitive vector, it is a translation vector. Now, what do you have? Let us look at the following, that is, consider this K PQR dot R L M N. Okay. What you get here is 2 pi times PL plus QM plus Rn. That is because of the orthogonality relationships that I had here, which is A dot A is equal to 2 pi, A dot B equal to 0, A dot C equal to 0, and similarly B dot A equal to 0, B dot B equal to 2 pi, B dot C equal to 0, C dot A equal to 0, C dot B equal to 0, and C dot C equal to 2 pi. Based on that, you can actually write down this one quite simply. So, what happens? So, this is very useful. So, if I had e to the power I k dot R L M N, then this is equal to e to the power I k plus k PQ dot PQR dot R L M N, or e to the power I k PQR dot R L M N is equal to e to the power I 2 pi into integer or equal to 1. Okay. So, what we have is that e to the power I q p q dot r e to the power I k p q dot R has the same periodicity as the lattice. This is very important, and I will come to the reasons why it is so important in my next lecture, but suffice it to say at this point that e to the power I k p q dot r PQR is KPQR is a reciprocal lattice translation vector. This particular function is a plane wave, and this plane wave has the same periodicity as the lattice. So, I will continue from here in the next lecture, and I will try to show you how I can construct Brillouin zone in any arbitrary case, and how it will be useful for dealing with energy band theory in 3 dimensions. Thank you.